So, hello and welcome to this beautiful day. Today, we're going to look at this beautiful theorem known as the Ramanujan Master Theorem, and this is due to the Indian mathematician Ramanujan. Ramanujan is known for literally anything integral series. Is everything. Everybody loves him, and his work is available online. You can go and check him out. Many theorem and series he has derived. So, but now we're going to look at this is Master Theorem, and here this is more like a formula that gives you the answer to many definite integrals, because we all know that definite integrals are very hard to compute, and we all pray for a formula that maybe, for example, the integral from 0 to infinity of f of x dx, maybe a formula that tells you what this is equal to. Though this is not true, it is not possible generally, but there are some cases whereby there may be some formula, and that is what this Ramanujan Master Theorem is all about. And it says that the Mellin Transform of any function, that is the integral from 0 to infinity of x to the s minus 1 times f of x dx. And this is called the Mellin Transform because usually when the limit of integration is from 0 to infinity, there are many transforms available. There are like the so-called Laplace transform of e to the negative xt. So for example, now the integral from 0 to infinity of e to the negative xt times f of x dx. This is called a Laplace transform, and is written in terms of t. It's a function of t, like g of t. This is called the Laplace transform. So you want to find a Laplace transform of any function, all you need to do is just take that function, okay, and multiply it by e to negative x and take the limit of integration from 0 to infinity, and then whatever you get gives you the Laplace transform. So I'm not aware of any formula, although there are many tricks to get Laplace transform, but I'm not aware of any formula for Laplace transform. On the other hand, there's a formula for Mellin transform, although this formula is not like general, because f of x has to satisfy some condition. But it says that if f of x satisfies this condition, then this Mellin transform of this function would be called gamma of s phi of negative s, where phi of x, for example, phi of n is related, I would say, is related to the series expansion. Is related to the series expansion of f of x. So you can recover phi of n from the series expansion of f of x. Now the question is that what should the series expansion of f of x be? Well, this is what it should be. It should be that f of x should be able to have this series expansion. It should be that f of x should be able to express as a sum as n runs from 0 to infinity of phi of n over n factorial times what? Times negative x to the n. So it should have a series expansion whereby there is a factorial in the denominator, and you should have a negative x to the n power. So if this is satisfied, then it is possible to get the Mellin transform of this function in terms of this phi of n. And the best way to master this is practically by solving a lot of problems with it. And of course, I'll try my best to solve like up to 10. I'll do up to 10 problems with this. So this probably is going to be like part 1 of the course. Then I'll do 10 more videos where I use this Ramanujan Master Theorem to solve some extremely complicated integrals. So please do check the playlist. You're going to see the videos. But for here, I'm going to just give like 2 examples where this theorem can be used. And one of those examples is this. Let's say you have, say, f of x is e to the negative x. So in this case, you have the integral from 0 to infinity of x to the s minus 1 e to the negative x dx. When we need to compute the Mellin transform of e to the negative x, okay, just like we have already discussed, for you to use the Ramanujan Master Theorem, everything would evidently depend on this expansion of e. So let's say we know that e to the x particularly is equals to 1 plus x squared over 2 factorial plus x to the third over 3 factorial and so on. So basically this is the sum as n runs from 0 to infinity of negative 1 to the, no negative of course, of just x to the n over n factorial. Now that means that e to the negative x essentially will be the sum as n runs from 0 to infinity of 1 over n factorial. Then you have negative x to the n power. Okay. Now you can see that if you compare this with the form of the Mellin transform, if you run the comparison test, okay. If you do the comparison test, you will see that this our phi of n here is equal to 1. So basically, the integral from 0 to infinity of x to the s minus 1 e to the negative x dx is going to be gamma of s times 1, because phi of n is here 1 here. So essentially this means that gamma of s, the gamma of s is the integral from 0 to infinity of x to the s minus 1 e to the negative x dx, and that essentially tells you, and this is basically the definition of the gamma function. This is how we define the gamma function. So here it is, it's more like we could actually recover the definition of the gamma function from just the Mellin transform. Okay, we could just recover the definition of gamma function from just Mellin transform. So basically the gamma function is just a special Mellin transform. Okay, and not that one, it tells you that the Ramanujan Master Theorem is actually a more general case of the gamma function. You understand? So this is a very standard result, but just to show you how important and useful this Ramanujan Master Theorem is. Another example we're going to look at is the case whereby we have f of x is equal to 1 over 1 plus x. So in this case now, you are looking at the integral from 0 to infinity of x to the s minus 1 over 1 plus x dx. Now this case here now is not too difficult to evaluate, because you can just get the series as this 1 plus x. The series expansion is basically the sum as n runs from 0 to infinity of negative x to the n power. So now notice that we know that f of x must be of this form. Let me put it in a box. F of x, let's do a different color. F of x must have this series expansion phi of n over n factorial before you have negative x to the n. So we are missing an n factorial in the bottom. So what we're going to do here is that we're going to multiply the top and bottom by n factorial. So we're going to get n runs from 0 to infinity of n factorial over n factorial negative x to the n. So you're going to have to write this as n runs from 0 to infinity of gamma of n plus 1 over n factorial negative x to the n power. So if you compare them, you can see that phi of n now would become gamma of n plus 1, right? By direct comparison, you can see that phi of n will become gamma of n plus 1. So basically now, we are now ready to write down the value of this Mellin transform. So basically the Mellin transform here, which is the integral from 0 to infinity of x to the s minus 1 over 1 plus x dx. This is going to equal gamma of s phi of negative s, which is going to be gamma of s, and then gamma of 1 minus s, because in this case we are going to put s to be minus. So we know this is to be the reflection formula, which is pi over sine of pi s. So now you can see that two standard results in the theory of definite integrals has been established using the Ramanujan Master Theorem. This tells you, or this should convince you, that this theorem is extremely important, extremely useful, and it's everything. In fact, I use it a lot. So for the next couple of videos, probably we're going to spend like 10 videos. I'm going to solve some really difficult integrals using this Ramanujan Master Theorem. So basically, we're going to try to find next. So next video I'm going to make, we're going to try to find the integral from 0 to infinity of x to the s minus 1 times cosine of x dx, and we're going to find the integral from 0 to infinity of x to the s minus 1, or even tan inverse of x dx. And we're going to do more problems, like a problem whereby it does not relate to Mellin transform, but we're going to find a way to configure the problem and reduce it to a form whereby we can use the Ramanujan Master Theorem. One case we're going to investigate also will be the case of the Poisson kernels, the integral from 0 to infinity of x to the s minus 1 over 1 plus 2x cos theta plus s squared dx. So please do subscribe and put on the notification bell, please, so that you can check the channel. We solve cool integrals. So thank you very much for watching, and please do subscribe to the channel. Bye. Have a nice day. Thank you very much.